So, our first speaker needs no introduction. It's Andreas Oschlies, and he comes to us all the way from GEOMAR in Germany. Thank you.
Thank you, Julie. Thank you, Heather, Mary, Alison. So it's a great pleasure being here. The atmosphere is wonderful. It reminds me of the last big meeting. I saw many of the older faces. That was the Jacobs synthesis, or the final symposium, I think. Well, let's start, and I don't want to spoil the good atmosphere here. I would like to point out a few problems that have come across during our work over the last about more than a decade, where we ran this collaborative research center, SFB 754 in Kiel and northern Germany. And this comes to an end this year, so we are looking for new collaborations, new initiatives to resolve all the problems, a few of them I will mention today. And the Global Ocean Oxygen Network on the left here, that's a new initiative as well, where we try to coordinate particularly observational work, data quality issues in terms, well, everything addressing oxygen change in the ocean. What is this about? This is oxygen in the thermocline, so the upper few hundred meters. On the isopycnal layer, we see these big pinkish areas, low oxygen waters. These are relevant for ecosystems, for biogeochemistry, nitrate loss, phosphate release, iron release from sediments. And there's lots of change going on. Right now, the inventory is tiny compared to the atmosphere, so it's 0.6% of the oxygen floating around in well, O2 form. This is pretty different from carbon or from CO2. So this is most of the carbon is dissolved in the ocean, and the atmosphere is the tiny part. The oxygen is just the opposite. So it's good news for us. Whatever happens in the ocean doesn't affect the air we breathe for the next several thousand years at least. Oxygen in the water, well, is filled into the ocean from the atmosphere by a gas exchange, oxygen uptake. It's transported, it's dissolved O2, and it's consumed everywhere by respiration in the dark ocean interior. There's some photosynthetic production on the surface layer that escapes to the atmosphere, but the deep ocean just loses oxygen via respiration. There's no internal direct oxygen source, so it has to be resupplied. What happens under climate change? Warming. So we know the solubility goes down. Oxygen uptake in the surface layer will go down, just as warmer water can hold less oxygen or less of any gas. Transport, we are pretty sure that slows down. So this is the transport of atmospheric oxygen into the dark interior will very likely, or that's what the models tell us, what some measurements tell us, decreases under global warming. Oxygen consumption, we are not so sure. So that depends on how much organic matter is produced in the surface layer. And this varies from region to region. So subtropics might go down, and high latitudes might go up if mixed layers change and so on. Light limitation is relieved. A look at the cross-section, the warm water sphere, the upper ocean. There we try to figure out what is going on, what has been going on over the last decades, and what will go likely on in the future. And these are isopycnals, so the upper thermocline here. There's some mixing processes, and there's ventilation of the subtropical thermocline. So these are the old classical Lloyd-Pawlowski-Stamol models. I think also many pre-OCB summer schools here in Woods Hole led to the development of all these concepts. Under global warming, we see some shoaling of isopycnals. So these are, well, I had the same outcrop. The density layers are different here, but overall, everything moves closer to the surface in the subtropics or tropical oceans. And we see some decrease of solubility because warming in the surface layers will lead to outgassing. So there's some oxygen coming out of the ocean. There's enhanced stratification, so that means less mixing, or less energy is the same amount of energy mixes less water in a more stratified ocean. So that affects oxygen. And if we assume winds are unchanged, all the subduction process, ventilation, transport remains the same, but now in shallower, thinner layers. So that means transport is faster, And that, in this conceptual view, at least leads to more outgassing of oxygen in the ocean, because that water that arrives in the tropics is fresher, is younger, has been transported faster, so it had less time to absorb respiration. So this is the concept we have. And now we try to underpin this by model results, at least. So this is one of our models. It's a coarse resolution, it's a UVic model in this case. We can simulate abiotic oxygen, so that just feels the heat and no biology. And this shows a decline almost everywhere. Some pockets in the North Atlantic where the ocean might cool in some areas, but everywhere else we have blue color dominating here, so that means an oxygen loss of this abiotic oxygen, or it could be argon. So this is the indication, direct indication of warming. And it's a few, well, it's a few micromolar, so it's significant. So this is several percent over this century. If we force the model, just with changes in CO2 levels and changes in radiation, but no changes in winds, we just assume temperature warming addresses stratification and solubility, then we get this picture, and this is an iconic picture already, I would say. We see oxygen declines in the high latitudes, but an increase in the tropical thermocline. And this is due to this faster ventilation in this more stratified, shallower thermocline that transports water faster to the equatorial regions where it can outcrop again and outgas the oxygen to the atmosphere. So that's what we see in typical models, more oxygen, high oxygen levels in the tropical thermocline. This is not what we see in observations. It's completely anti-correlated. So this is an observational estimate in the at 300 meters depth, same color scale. Blue means oxygen loss over the last, this is now 50 years where we have good observations, or relatively good observations. And this shows dominance of blue color. That means oxygen decline in the tropical oceans. And our models, I can't go back here. So this model showed an increase if we turn on the heat only. So anti-correlated. And this is in fact what, these are all the CMIP5 models. You don't see much, you shouldn't see, but if you look at the tropics, it's dominance of red colors there. And so all CMIP5 models, or the average CMIP5 model shows an increase in oxygen in the subtropics and tropical oceans in the thermocline. So this is anti-correlated with the observational estimate over the last 50 years at least. How come? So we have tried, well, typical issues you look at when you are a modeler, mixing. It's heavily parameterized, and we don't know how to do that carefully, at least not at all in coarse resolution climate models. And so we played around here with different diapixel mixing coefficients. We can slightly change patterns, but we don't change the color. It remains red in the tropical ocean, and we think mixing alone cannot explain this discrepancy. Models produce an increase in oxygen in the tropical thermocline over the last 50 years. Observations don't show that. We have some success if we change also the stoichiometry. So if we assume carbon-CO2 fertilization of algae, so an increase in C/N ratio, that means an increase in respiration, so basically more junk food, higher carbon content, and then you have to breathe more to digest that. There are some animals and bacteria, and they consume then more oxygen at higher CO2 levels for the same nutrient supply. So this at least gets the Eastern Pacific here in this blue color region, but it's not a great success, and the mechanism is questionable as well, or the way we parameterized it as well. So we can't claim any significant progress here. And progress can only be claimed once we use observed winds. And this is the first indication winds are really important for oxygen in the thermocline. And these are the same, again, the same model. This model, again, was red field stoichiometry, so no carbon fertilization effect. But here we use reanalysis winds, the core reanalysis winds. That's a slightly old study. But we are redoing this with the modern, new reanalysis data and get similar figures. This at least shows blue color here and in the Eastern Pacific in this version as well. Both model runs have the same core reanalysis since 1958. And that fits nicely to the observational period, 1960 to 2010, where these observational estimates were taken from. But they have a different spin-up. So this one uses NCAR NCEP climatology prior to 58, and this one uses core climatology prior to 58. From 58, they are identical forcing, identical CO2 emissions, identical winds, identical solar cycle. But the results here are completely different in the Western Pacific, and that tells you there's some legacy of winds prior to our observation period. And this is important to know, since that's what we usually hide in our model spin-ups, and where we also don't have very good observations. Now there are good attempts to go back into the naval archives to get better wind products from the years or decades well before the 60s, where our good oxygen observations really start. And we even have, well, longer backwards going oxygen observations from the meteor observation campaigns in the early 20th century. So this is, shows the relevance. There are things, there's legacy in the ocean and ventilation, of course, and oxygen traces, biochemical traces that are moving around already for several decades in the thermocline, and that affect changes in oxygen we observe today. So it's not just what happens today, but what has been subducted a number of decades ago. Conclusions, first part here, the oxygen deoxygenation, oxygen decline, the tropical thermocline is not well understood. There's lots of natural variability, as indicated by these observed winds that manage to get the right sign of oxygen change in our models. So winds play a dominant role, but there's also overlap of natural variability, anthropogenic forcing, and also this legacy of wind changes or climate changes well before our observational period where we started having good oxygen measurements. Now, the total picture, vertically integrated oxygen loss. Not only the thermocline, which might be more relevant for us looking at ecosystems, or for people looking at ecosystems. And this is, again, by Sümke-Schmidtke analysis, showing the vertically integrated oxygen loss. Unfortunately, the color scale is inverse here. Now, you have, it's early morning. I've trained you to blue is oxygen loss. Now red is oxygen loss, okay? And it's red almost everywhere. So vertically integrated, the ocean loses oxygen almost everywhere. Interestingly, in the Arctic, this hasn't been realized, or at least not by me before I read the paper. Equatorial Pacific, yes, we saw that in the thermocline, and there's also oxygen loss going on deeper, and in the Southern Ocean, interestingly, as well. This is what the models have always shown us. There was oxygen loss in the in the high latitudes, but this is, I think, the first observational map showing there's, well, key regions of substantial oxygen loss there. Interestingly, there's no significant loss in the Atlantic if we integrate over the entire water column. So there's compensating effects there over the last 50 years, over these 5 decades. Integrated, the ocean loses about 1 petamole per decade, according to this observational estimate and a few other estimates as well. And if we again look at the CMIP 5 models, and I'm curious to look at the next upcoming CMIP 6 models, they don't show this 2% decline that Sümke-Schmidtke and others derive from observations. They show, well, factor 3 smaller or slower decline of oxygen inventory in the total global ocean. And this is a huge discrepancy. So if we would convert oxygen to carbon, we would be really low. But it's not really related to carbon, it's related to ventilation, I think. But still, it's a huge mismatch, and none of the models gets close to the data or to the data-derived estimates. And here's the NCAR large ensemble that we will hear more about, I think, in the next talk. So this has even still slower decline, and maybe there are some ensemble members we can look at to better understand why there's such an underestimate. So this is a huge first-order problem I think we have to resolve. And this is my attempt here. The vertical axis is, again, the oxygen decline observational estimate, and these are the CMIP models. One model was there with an incomplete spin-up. That's, I think, the Italian model. I discarded that only 300 years. I think I discard that in the future. These are all our attempts to get a larger oxygen loss over the last 50 years. And we failed, you see. We got some minor improvements, some minor increase in the speed of loss, but there's no way we can explain this. And so the question is, what is it? Is it solubility? That means heat uptake is wrong? Or is it ventilation? Or is it biology, respiration? What is wrong? And it's a factor 2 to 3, or well, at least 2 to 3. Okay, you can look again into the data. This is the global profile of oxygen loss, the black, the total curve. Zero line is here, and there's a small loss to the left, 6,000 meters. The red line is the solubility part, just if you would take the water, measure the temperature change, and equilibrate it with the atmosphere. So we see in the surface layer, the total loss, the solubility loss is faster than the observed total loss. So apparently there's something pumping in oxygen and compensating for the warming effect itself. In the thermocline, almost all the total loss is explained by solubility change in the global average. In the deep ocean, almost none is explained by solubility. So there's something else must explain it, circulation or respiration. And we can look into the models again. And there we see the total observed oxygen loss, huge. None of the models gets close. But the solubility part, that is, here's the first sign of relief. Simulated almost, well, pretty well by most models. And that means the heat uptake is simulated well. So that's what the models were made for. It's climate models, and they were made to simulate global warming, heat uptake, and carbon uptake. So they are not so wrong as it might appear at first sight if we look at oxygen changes. Something else must be wrong, so circulation or biology. And to look at this, I had a few regions here in this analysis, and I looked at different depth horizons. Let's start with the Equatorial Pacific. Bless you. The observation estimate for the deep ocean, deeper than 1,200 meters. That's the blue bar here. And on the x-axis are just the different CMIP models, CMIP5 models. And these are the black bars. And almost none of the models gets into the right range of oxygen loss in the deep ocean. The blue bars are far too short to reach down to the observed levels. Same in the surface layer in the Pacific. That's what we have already seen in the thermocline. Even the sign is wrong in most models. So the deep ocean is a problem, in the southern ocean as well. There's one model, the French model, that hits the deep ocean oxygen change in the Antarctic. All the others don't reach this observed estimate. They're far too short. Subtropical South Atlantic, again, none of the models gets the deep ocean oxygen change derived from observations right. They are not so bad on the surface ocean, upper 1,200 meters, but the deep is really a problem. So deep ocean oxygen change, if that is derived correctly from observations, then our models have a huge problem. So that might be ventilation. It's probably ventilation. And a recent study by Ballard just came out last week. I'm not sure whether the authors, yes, Anand, I think. That showed what happens if you change isopycnal diffusivity in the models. Again, a mixing parameter we don't understand very well, or we can't constrain very well. There are different strengths, sluggish, more intense, and this is, well, the same, basically same parameterization, so on average. And they show when you have more isopycnal ventilation, isopycnal mixing, there's enhanced oxygen loss. Here again, sorry, blue is again loss of oxygen. In the high latitudes, in the deep 3,000 meter oxygen change that you don't see if you have typical values we use in climate models right now of slower isopycnal mixing. So this is an indication that deep ocean ventilation might be pretty wrong in our current models, and oxygen might help us, help the physicists to get it to improve it. So wherever we look, models underestimate oxygen decline. They also underestimate seasonal variability, El Nino variability, always by a factor 2 to 3. So it's a systematic problem we have, and we haven't resolved yet. There's some good agreement in the upper oceans, upper 1,000 meters, except in the tropical Pacific thermocline, which might be due to internal variability. The key problem, I think, is that the deep ocean, it's not very well observed. So observational estimates maybe they have huge error bars, they may be wrong. Maybe instrumental problems as well. But here we really have a discrepancy we should be able to address in the next few years, I hope. And it can be on both sides. It can be on the data side, can be on the model side. And I think we need to understand the impact of circulation changes in the deep ocean. There are many other approaches, CFC or anthropogenic traces, abiotic transient traces, that we can use and should use. And, well, we talk about biogeochemistry here, so there may be biogeochemical feedbacks as well. Oxygen-sensitive processes, denitrification, sediment interaction, that all might affect oxygen, even on timescales of a few decades. And I ask you to help us solving this problem. And we had our big program running for 12 years. We haven't been able to resolve this. And it's, I think, but we have been able to point to the problems, and now we need you. Thanks for your attention. Just one.
Well, actually, we have time for a few questions, right? So we have time for a few direct questions for Andreas, and I'd ask you to wait for the microphone so that everyone that's listening on the web can hear the question, and we'll get our next speaker set up while Andreas is taking questions.
Thanks, Andreas, for the nice talk. You mentioned the models are underestimating the deoxygenation in the deep ocean, and that's tied to the circulation. Do you think it's because they're getting the mean state circulation wrong in the deep ocean, ventilation of the deep ocean, or is it because they're misrepresenting the changes in circulation in the deep ocean?
Well, the mean state is wrong as well, but this is all about changes, so decadal changes, and I think that we see the models don't get it right. So they are probably, I think we have selected for the very sluggish, well-behaved, or not the models that are not too ill-behaved. They don't have a high variability, so they are usually thrown away. They're difficult to publish. They do strange things, and there's some convergence to models that are smooth and very dissipative. I think there's some natural selection for those models. And that might explain why we see, even in seasonality in the thermocline, El Niño variability, too low amplitude and oxygen changes everywhere. And so I encourage the young students, PhD students and so on, to don't throw away your model if it shows a large variability. I think that's what we always did in our career. And, well, it's... you may have it easier to publish that what is consistent with other bulk estimates, but the interesting part is in the variability, and I think there we should encourage ourselves to look more. That's the interesting stuff that's happening, and we shouldn't be too afraid of very variable. Well, I evaporated the ocean many times, but maybe sometimes it was almost right, and I shouldn't have given up so early there, I think.
Oh, okay. Hi. I really liked your talk, and my question is, you talked a lot about the circulation changes. You could also have a circulation change and a change in the export rate, so you have kind of confounding things. I'm wondering if you've thought about the magnitude of that export number change that would have to account for the observations, and if it's reasonable.
It would be huge. So I think export change can explain about 10% of the total observed changes, about maybe 20%, but that would be 100% export change. So most of it must be by circulation. Well, there's DOC. If that is accessed suddenly, that could give another 20% maybe, but it can't explain everything.
Hi, Andreas. Thanks for your talk. Continuing on to the exports, how about vertical migration of zooplankton and respiration? Is that part of your model? Could that be?
It's not part of our models here. There are some models that do have that. And that's an interesting point. So whenever that can change with changing stratification or expanding oxygen minimum zones, that is a huge potential to shift the oxygen consumption vertically. It doesn't change the global integral, but it can change vertical structures of oxygen loss. Yes. And I think there are some feedback process even just around oxygen minimum zones where the respiration might just occur around the oxygen minimum zones and therefore lead to further expansion. So this is an interesting interaction between biogeochemistry and ecology. Where does respiration occur?
All right, well, let's thank Andreas, and hopefully we'll have time for more questions in the panel later.